So, hi everyone. Today we're gonna make a presentation about our report. We are mainly study the Elizabeth Tower and Steinway Tower, and I'm Kevin Howe, and I'm gonna provide some basic information about our study. And for Jackson, he'll do something about our methodology, and Williams will provide the result, and Rebecca will do the summary. Yeah. And first, I'm gonna introduce our motivation. So on one hand, we study the Elizabeth Tower. As we all know, it is located in London, and it stands at the north end of the Palace of Westminster. And it's really famous. It's a really famous tourist attraction, and it's also recognized as the national symbol of the UK, and it's also part of the UNESCO World Heritage Site. Yeah, and that's about the Elizabeth Tower. And for the Steinway Tower, on the other hand, it's located in Midtown Manhattan, New York City, and it is completed in 2021, which is a brand new structure. And this structure is mainly famous for its extreme slenderness, because it has a height to width ratio of about 1 to 24. So it's known as the thinnest skyscraper in the world. And yeah, so our objectives, the objective of this research is to develop finite element models of these two structures, and we want to compare their natural frequencies and harmonic responses under identical wind conditions. Since we all know this, the Elizabeth Tower is a really ancient building, while the Steinway Tower is a modern one, where we want to identify how their materials difference and structural systems difference drive their different behavior under similar conditions. So here is some detailed information. So for the Elizabeth Tower, it's about 96 meters tall with a roughly 12 meter square base and 11 floors. And there are four clocks on each side of the building, and each of the dials is about 7 meters across with a minute hand around 4.2 meters long. And this tower is built by uh, three types of stones mainly, and for the Anston and Clipsham stone outside and the Caen stone inside. And it also houses a 13.7 ton Great Bell, which is known as the Big Ben. So there's something you have to pay attention to. The Big Ben stands for the Great Bell inside, not the Elizabeth Tower itself. And for the Steinway Tower, as I had said before, is completed in 2021, and the formal name is 111 West 57th Street, and it's about 435 meters tall with 84 stories. Uh, and it's built with high-strength reinforced concrete, shear walls, and a glazed terracotta, which is a kind of clay, and bronze and glass facade, and a near top tune mass damper about 800 short tons, which is about like 726 metric tons, I think. Yeah, and the damper is built to keep it steady in strong winds. Yeah, and that's all about the background information. So now let's welcome Jackson for the methodology part.
Hi, I'm Jackson. I'm responsible for introducing the modeling and the method we used to analyze these two buildings. Due to a lack of original blueprints of the buildings, we estimated the dimensions of both buildings through figure measurements, which I will show later. These two pictures here are not drawn to scale because the skyscraper is about 4 to 5 times the height of Big Ben, and if that were to be in scale, you can hardly see Big Ben. Uh, Also, I tried to imitate Big Ben's Gothic structure a little bit. Gothic structure is known for its um, thinness and angles, straight lines, uh, and slenderness, which is actually not so slender compared to the modern skyscrapers. But for the base here, I used structure like uh, triangles emerging from the wall so that it can show it can kind of resemble the Big Bang instead of just building a straight tower that maybe no one can understand what it represents. The model is hollow for Big Bang because we are able to calculate the thickness of the wall through pictures at different angles of the building. We actually found a set of pictures which allows us different angles and so that we can analyze the building uh, in and out. So uh, we figure out the wall thickness is about 0.9 meters, which is reasonable based on our understanding of normal wall thickness. However, we had to construct a solid model for the Steinway Tower because we lack information of the hollow space distribution inside the building. We only found the total amount of floor in in a 2D dimension. So we only know how much uh, area, but we didn't know anything about the height of each floor. Our materials. A big difference between the two towers is their building materials. Big Ben is built from limestones with a density of 2,600 kilograms per meters cubed, a Young's modulus of 50 gigapascal, and Poisson's ratio at 0.2025. Steinway Tower is built from mainly concrete with steel structure. Concrete has a density of 2,400 kilograms per meter cubed, Young's modulus 20 gigapascal, and Poisson's ratio 0.2. The major difference between these two materials is their Young's modulus, which is a stiffness measurement. And thus, that can possibly explain why Big Ben is more stiff compared to the structure of its height. Um, Understood in another study of 163 buildings best fit curve. Our methodology. This is, by the way, this is the picture I'm talking about when I said we did measurements to construct a model of Big Ben. We actually measured more than this, but the thickness is done on another picture, so I didn't show it here. We did find, however, XYZ dimension for each floor chart on Steinway Tower, so that that model should be more concise. Sorry, yeah. Anyway, we ran model analysis of to understand the natural oscillation of the structure and harmonic frequency, which imitates an external force applied on the towers. We input calculated density because the actual volume differs a little from the volume of our models. So that and density is not a deciding factor of the stiffness, and and thus it is okay to use a calculated density when we know the volume is not exact. We also use the Young's modulus and Poisson's ratio of the materials, respectively. We applied the strongest wind force ever in the area to perform harmonic frequency analysis so that we can understand how the building performs under extreme conditions. We conducted the analysis at zero damping for Big Bang because it is designed without a damper. And this is an extreme case because normal buildings don't wouldn't have a zero as its damping ratio. However, Big Bang, I think, gives a pretty good result against external forces, despite its given at a zero damping ratio. And we studied the effects of dampers by applying damping ratio of 0, 0.01, and 0. Sorry, I think that's 0.2 for Steinway Tower. Next, William will introduce our results.
Uh, Now I'll talk about the comparison between the Big Bang and the Twin Tower. The, the first is about the frequency range. Big Bang has a wider frequency range, up to 8.869 Hz, and the Twin Towers is narrow one up to 4.584 Hz. The Big Bang and the Twin Tower have similar frequency between mode 1 to 2 and 3 to 4, but in the in the Twin Tower, 6 is a little bit greater frequency than the 5. And this is the comparison of the amplitude change. For the Big Bang, the amplitude surged sharply to from a peak at a maximum displacement of 5.8 to multiply 10 degree of 5 negative 5, and at about 4.6 Hz. For the string tower, the amplitude has a maximum displacement of 0.778 meter at about 0.3 Hz, and then it consistently decays. And for the phase angles, the phase angle of Big Bang is stable in the early stages and mutates in its high frequency band near 6 Hz. The phase angle of the swing tower mutates at low frequency, about 0.3 Hz, and then tend to be stable. And this is our graph of the analysis. Is the Big Bang tower, and is the string tower. And now I will talk about the difference between two different damping ratio. The first is 0.1 and the second is 0.2. In the amplitude, the damping ratio of 0.1 has maximum amplitude of 0.70884. Damping ratio of 0.2 has a maximum amplitude of 0.4778. Higher damping ratio suppress amplitude. However, they try little effort on uh, curve geometry. And in the phase angle, for both damping, phase angle changes rapidly at low frequency than stable. At damping 0.2, the change is quicker, and the stable phase angle is slightly lower. Higher damping stabilities phase earlier. So in conclusion, higher damping ratio suppress amplitude more, stable phase earlier, and restrict structural vibration more. And this is the difference between damping ratio of 0 and 0.1. In amplitude, the damping at 0 uh, with higher initial peak, extra small peak at 1.5 Hz, and even decay. In damping 0.1, lower peak suppress the extra peak, more uniform decay. In phase angle, damping in 0 with rapid lower frequent about 0.3 Hz jump, then stable high value. In damping 0.1, earlier greater jump, lower stable angle. So in conclusion, damping rates from 0 to 0.1 reduce amplitude peaks, smooth decay, uh, moderate phase jumps for calmer structural vibration. Uh, the next is about the summary.
I'm Rebecca. I'm going to make the summary and the conclusions. And our data reveals key findings. The first one is frequency response variation. Big Bang exhibits significantly smaller frequency variations under applied forces compared to the Steinway Tower. Notable differences include frequency range, distribution, consistency, amplitude, and phase, suggesting distinct dynamic behaviors between the two structures. And the second one is structural integrity insights. And despite advancements in modern construction techniques and certain aspects, stability is influenced by multiple factors, including material composition, height, and design with historical buildings, potentially benefiting from robust traditional methods. And in conclusion, the ANSYS model highlights that while modern skyscrapers like Steinway Tower incorporate innovative technologies, some historical structures maintain exceptional resilience. And this underscores the importance of integrating lessons from traditional engineering with contemporary practices to optimize future architectural designs. Thank you.
Hello everyone, this is our presentation, and we will show the results we achieved over the past few days. Now let me briefly introduce the motivation behind the construction of One World Trade Center. One World Trade Center, completed in 2013, stands 541 meters tall and is the tallest structure in the United States. Its hybrid structure system and symbolic significance motivate a deeper exploration of its performance under dynamic laws. Next, extant study mainly focus on architectural design and materials, but like detailed investigation on dynamic responses. This project addresses that gap through model and harmonic response analysis. A simplified model was developed based on well-designed parameters and analyzed using ANSYS to evaluate structural vibration behavior under when included harmonic excitation. Well, this study is driven by the three mainly objectives. First one is analyze the dynamic characteristics of one World Trade Center using model analysis. In addition, evaluate the structural response under when included harmonic excitation and examine the influence of different damping ratio on peak displacement and resonance behavior. Okay.
Okay, let me introduce the background of our One Trade Center. One Trade Center utilized a hybrid structure system. At its core lies a reinforced concrete staff that provides a primary lateral resistance, while surrounding steel moment frame offers additional stability against wind and seismic loads. And we can see clearly that the engineering used three main materials to build the One Trade Center. The ultra high performance concrete at the bottom of World Trade Center and high strength concrete at the bottom of One Trade Center. And at the top of One Trade Center, the engineering just used structural steel. And we can see the properties of the three respective materials. And the high ultra high performance concrete at the bottom of One World Trade Center, we can see it has a greater density since it have to undergo higher force, and its Young's model is greater. And at the top of the One Trade Center, there is structure steel, since at the top of the One World Trade Center, it will undergo higher wind speed and to enhance its structure. So the density of steel is really great. By the way, the Young's modulus means that when it undergo a same force, it will deform a little. To ensure accurate stimulation, the structure is modeled using three primary materials. Yes. And for second page, I'm going to introduce the three main functions we use. First is function T. Mass multiple the second derivative of displacement, we know that is acceleration. Mass minus mass multiple acceleration is force, and second one is the damping coefficient minus the damping coefficient plus the speed. This is the damping force. The first K multiple X is the coefficient of stiffness, multiple the displacement, and we know that is the recovery force for the yes. For the second equation, we can see compare with the first equation, there's no C multiple the first derivative of displacement. So this equation is no damping force. Yes. And for the third equation, it is just a normal equation for the simple harmonic motion. We know that the displacement T equals equals amplitude multiple cosine angular velocity multiple time minus the initial phi. Yes. This equation lies the foundation for subsequent calculations.
This slide outlines the simulation methodologies used in our project. First, we construct a simple models of the one trade center using the reference dimensions and import it into ANSYS. Second, the material properties such as Young's modulus and Young's modulus, Poisson ratios, and the density were assigned to different regions based on the designed specifications. Third, the mesh was generated to ensure the computational accuracy, and the appropriate boundary conditions were applied to simulate realistic constraints. Both the wind load was implemented according to the ASCE 712 guidelines. The wind acting on the windward phase on this on this structure. Finally, we proceed the simulation results to extract key outputs such as displacement, stress distribution, and mode shapes. Now let's look at the two nature models of the One World Trade Center with sphere. As shown in this figure, you will see model 1 corresponds to a translation model in x direction. With the with a natural frequency of 0.11415. This def These deformation shapes indicates that the building sways almost along the axis. The model 2, on the other hand, is also translational model, but it occurs in in the direction with a slightly higher natural frequency of 0.14016. The direction of the deformation changes, but the model shape similar remains similar in the form. These two models reflect the basic vibration characteristics of the tower, and the close values of the frequency indicates that the structure have a nearly symmetrical stiffness in two horizontal directions. Next, we examine the Model 3 and Model 4, which represent the higher vibration of the tower. The Model 3 frequency is 0.47858 and shows the lateral sways with notable asymmetrical deformation along one horizontal axis. The Model 4 with a very close frequency of 0.4792. It shows a similar deformation in the perpendicular direction. These symmetrical in-model shapes and frequency suggest the building have nearly uniform stiffness in the both directions. Finally, the Model 5 and Model 6 also shows the higher vibration. This frequency 0.7528 and 0.75296 are very close. This again reflects the geometric symmetry of the tower and result in a pair of models. It is also similar to what we observed in Model 3 and Model 4. To summarize the natural frequency and the model shapes of the One World Trade Center with sphere, we observed 3 pairs of models, Model 1 and Model 2, Model 3 and Model 4, Model 5 and Model 6. These are all occurred by the symmetrical geometry of the tower. Additionally, the maximum normalized deformation also occurs at the tip of the sphere. So it indicates that it have a high sensitivity to the dynamic efforts like windward.
Okay, as far we have completed the model with the spire, so to discuss and get a result with the model accurately, we continue to model without spire. As you can see, we also completed the same, almost the same order as the same before, and we get 6 model for the model 1 and the model 2. They also have the same frequencies, almost the same. As you can see, model 1 and model 2 exhibit the lateral translational motion along the orthogonal directions, similar to 4 model with the spire. And however, the natural frequency are higher, about 0.2, 0.54 Hz compared to the
0.14 Hz when the spire is included. This clearly indicates that removing the spire will increase the overall stiffness and also reduce the dynamic flexibilities. And this is our Model 3 and Model 4 without the spire. Both modes of demonstrate the higher order lateral bending with frequency of 0.986867 Hz and 0.098789 Hz respectively. These results are very close, indicating another degenerate pair, again due to the geometric symmetry of the structure. And this is our Model 5 and Model 6 for the structure without the spire. Model 5 with a frequency of 1.7278 Hz shows a high order lateral bending mode. And say Model 6 with a frequency of 109,362 Hz exhibits a different deformation pattern, likely associated with the torsional or coupled vibrations. As the frequency increases, the deformation becomes more compressible, highlighting the dynamic nature of the structure even without a spire. Okay, so we finally get the total results for the model without spire, as you can see in the figure. Model 1 and Model 2 have very close frequency around the 0.2 Hz, indicate the translocation vibration along the X and the Z axis. Model 3 and Model 4 also have the approximate 0.9878 Hz. And so they also have the couple translocation and the minor torsional behaviors, especially along the axis, y-axis. Model 5 and 6 with higher frequencies involve more complex coupled deformation, suggesting the higher order dynamic response. It is worth noting that degenerate model pairs still exist due to the geometric symmetry, even after the remove of the spire. The maximal deformation is generally larger in the lower modes, which is typical for the old structure. To figure out what's the difference for the model with and without spire, we conclude the two graphs together. The left one is a model with spire and the right one is the model without spire. The spire presents a comparative analysis of the model frequency and the normalized deformation between the structure model without and without spire. In all models, the structure without the spire shows a high natural frequencies, indicating a stiffer dynamic response due to the reduced height and mass. Conversely, the model with a spire consistently exhibit larger normalized deformations, especially in the higher models. For example, Model 6 and Model 6 to 3 to the 6. This confirms the greatly flexible and dynamic sensitive introduced by the spire. Despite the differences, model pairing persists. For example, model 1, 2, 3, and 4, due to the inherent symmetry of the tower. In summary, the spire significantly softens the structural dynamic behavior, reducing its frequency while amplifying the deformation, especially at the top of the building. Okay, the result clearly indicates that the addition of the spire significantly altered the dynamic behavior of the One World Trade Center. Especially, it leads to the decrease in the natural frequencies and a notable increase in the maximum normalized deformation. It implies a softer and a more flexible structural response. Furthermore, the first two modes in both cases consistently displays the pure translational motion, and it primarily in the x and the z axis direction. In contrast, the higher order mode exhibits the coupled translational and translational behavior, which become more evident in the width spire configuration due to the added mass and geometric asymmetry. And this highlights the critical influence of the standard architectural extensions like the spire on the model characteristics of the tower building and the importance of considering them in the dynamic analysis. Okay, you can see we further conduct some harmonic response analysis under the wing excitation. This further evaluate the tower behavior under the realistic environment conditions because as you know, in the real environment, there are some external forces like the wind. So we calculate in these models. As illustrated in the figure, sin lateral wind force was conducted in this model. This method enables the investigation of the structural steady state, a response to the periodic wind loads. It can provide some critical insights into the resonance risks and potential vibration amplifications near the natural frequencies. So let's continue. Okay, after conduct some wind load at the build model, we generate this graph after analysis this model. As you can see, this figure presents the harmonic response result under the sine wind loading. The upper plot shows the amplitude of the displacement as a function of frequencies, while the lower plot illustrated the corresponding phase angle. Notably, the amplitude graph reveals the pronounced peaks at approximately 0.14, 0.48, 0.7 Hz. You will surprisingly find is that the frequency at the peak here is very close to the frequencies we studied in the model 1, 2, 3, 4, and 6. So this frequency align well with the natural frequency previously identified through model analysis. It confirms the structural susceptibility to resonance under periodic wind excitation. Okay, the harmonic response analysis under wind excitation reveals that the tall structure like the One World Trade Center are susceptible to wind-induced resonance. Significant amplification of displacement occurs when the excitation frequency approaches the structure's natural frequencies. This finding emphasizes the importance of incorporating damping mechanisms or refining structural design to reduce the resonance effects and ensure the dynamic stability. So to avoid that situation of the resonance, we continue to study how the damping ratio will influence the building stabilities. So as you can see, we first introduce the equation of the damping ratio. As you can see, C is actual damping coefficient and CR is the critical damping coefficient. This ratio directly influence how this structure responds to the dynamic excitation, such as wind or seismic loads.
it can determine whether the system is under damped, critical damped, or over damped. Okay, we set four different damping ratio for these buildings. It's noted that we use model for the building with the spire. So it's a four model. Okay, so when the damping ratio equals to 0.01, we can get the maximum amplitude about 40.144. And when we increase the damping ratio from the from the 0.01 to the 0.05, you can see the amplitude decrease from the about 4 meters to the 1 meter. And for the frequency is remains constant. It focuses on the first natural frequency. As illustrated in the result, if we increase the damping ratio, so we can get a reduction in the maximum displacement amplitude, and the corresponding resonance frequency remains nearly constant. So this behavior demonstrates that higher damping ratio will improve the structure's energy dissipation and capacity. It can effectively minimizing the resonance when induced vibration and contributing to the overall dynamic stability of the system. Okay, that's all. Thank you for your listening. I'm Bruce. I will introduce the One World Trade Center's motivation and objectives.
And I'm Nicholas. I'm going to introduce the background we study and the basic equations we use to analyze the one-way trade center's function.
My name is Yu Shijie. I will introduce the method and some result concerning this project.
Okay, I'm Yuchen Lou, and I will continue to our method of our model, and we also get some result from this graph, and I will talk about the result we get from our model, and talk some method to improve our model. Thank you.